Really interesting. Everyone keeps telling me that Julia has this auto differentiation thing. How does that work? My understanding is this is the talk that will explain how to get started with auto differentiation in Julia.
Exactly. So we are Guillaume Dalle and Adrian Hill, and we're going to talk about gradients and give you a little tour of the automatic differentiation ecosystem in Julia. So we're going to start with a very, large, high-level overview of automatic differentiation, what it is.
Mention where we can find the slides, maybe.
Oh yes. So if you haven't scanned the QR code yet, then I will give you a couple of seconds to do so.
And the link, is it on? The link is also on the pre-talks page for the talk, for the slides.
All right. So we're going to tell you what AD is, the state of the Julia ecosystem, and then move on to a high-level overview of how it works, how to use AD in Julia, what sort of common pitfalls are and how to avoid them. And we're going to end on a high note by showing you a project we've been working on over the past month, which is DifferentiationInterface.jl. All right, so let's get started. So maybe the most high-level idea is to talk about what a derivative is, and the most simple mental picture you can have is that it's a linear approximation of a function around a given point. And why do we need this? Derivatives and gradient-based optimization are essential optimization, and especially in machine learning and deep learning. And when we talk about functions, I should emphasize that more specifically, we're talking about functions expressed as programs. And in an ideal scenario, you wouldn't even need to do that much to compute derivatives. With automatic differentiation, you should ideally get them automatically. All right, so when we talk about the state of AD, we want to first emphasize that there's three different types of people who use AD. So first of all, we have package users who want to differentiate through functions that are exported by packages. Then we have package developers who write those functions and who want to make them differentiable. And finally, we have backend developers who make these awesome packages, these awesome AD backends that we use. All right, so let's get started with the user experience. And I would like to sort of motivate this by comparing it to the state in Python. So let's say we are a user and we want to use, we need to make use of two packages, a package foo and a package bar. So the way you would do this in Python is that you would first pick a framework, which is basically a domain-specific language. So the big ones are PyTorch, TensorFlow, and JAX. And once I've selected my sort of framework, then I hope that my packages are implemented in this framework and I can use them. So in some sort, users of these packages have a sort of three-language problem going on. So within Python, they use a framework which in itself is written in a sort of third language again. And sort of the crux to this is that packages need to be rewritten for each of these frameworks. But once you're in such a framework, you're basically assured that packages will be compatible. And you can be sure that jax.grad works on a package that has been specifically written for JAX, for example. So in many ways, users of these frameworks don't need to understand AD at all. In Julia, we have some advantages. So in Julia, only one foo and one bar package need to exist. And this can be a big advantage because efforts on these packages can be centralized. However, compatibility with the backends is left up to the package developers and must be documented because otherwise users don't really know which backends work. And it also puts some burden on the user because it can be sort of hard to understand constraints that follow from these backends. And ideally, things should just work. So let's talk about the developer experience as well. In Python, once again, things are sort of simple. You just pick a framework and then you write code for it. Whereas in Julia, you typically first write code. So this might be some physics simulation. And at some point, you decide, oh, I would like to compute gradients over my simulation. How do I make this differentiable? And you select one of over a dozen backends. There's a very nice overview over at juliadiff.org. But one of the problems is that all of these backends come with constraints. And this is sort of the case for both ecosystems, but a big difference, which hopefully I convey on the slides, is that these constraints point in different directions. So in Python, frameworks such as JAX also have constraints. For example, they don't allow in-place mutation. But since you picked your framework, you're usually aware of these constraints before you even start to write your code. And in Julia, these constraints can sometimes come after writing your code. So in this example that I just gave you of a physics simulation, you might have to rewrite your code to make it differentiable with some of the backends. And something that makes this even harder is that some of these constraints conflict with what we think of performant Julia code, right? So usually we want to reduce allocations, we want to do in-place updates, but with some backends like Zygote, this in-place mutation is not good. So there's a lot of folklore and hidden knowledge on how to work around these things, and Guillaume will dive into this more deeply. But the question is then how to choose an AD backend and how to make it work on your code. And to understand these constraints, we will quickly tell you about the different kinds of AD systems. So there's 4 flavors of differentiation, let's say. The first one is the manual one, where you put in your blood, sweat, and tears, and manually write a gradient function that computes gradients, derivatives, whatever you want. The second one is the numeric approach, so basically finite differences, which is very flexible and can work on almost any code. Thirdly, we have symbolic differentiation, or basically computer algebra, where you give a symbolic formula for your function and get a symbolic formula for your derivative function back. And finally, we have automatic differentiation or algorithmic differentiation. So this is sort of what encompasses forward and reverse mode. And there you pass a program and get a value for your derivative, gradient, Jacobian, whatever back. Okay, so let's dive a bit deeper into this fourth point, which is automatic differentiation. And there's more or less 3 key ideas here. So programs are compositions. So this can either be a sequential chain or directed acyclic graph of elementary functions. And the multivariate chain rule then tells us that the Jacobian of such a composed function corresponds to the product of Jacobians of these individual functions within. And as you can maybe already see when you look at this equation, this can be quite memory intensive. So if we were to save all of the Jacobians of some large language model with millions of parameters and very large hidden activations, maybe we wouldn't even be able to save all of these Jacobians. So what we do instead is, instead of fully materializing them, we work with matrix vector products. So Jacobian vector products and vector Jacobian products. And if we work with the former, with Jacobian vector products, which are also sometimes called push forwards, then we end up with forward mode AD. And in here we basically accumulate these Jacobians from the right. We've added this parentheses to emphasize that we're always working with products of Jacobians and vectors. And as you can see here, this accumulation happens in the same direction as sort of the evaluation of our function. And we can therefore evaluate these Jacobian vector products in one forward pass through a function, which gives forward mode its name. And the sort of gist of all of this is that if we evaluate matrix vector products with unit basis vectors, for example, the eth unit basis vector, then this returns us the eth column of the Jacobian. So if we have an m times n Jacobian, computing the full Jacobian with forward mode requires n Jacobian vector products. And the special case of this is, of course, if you have a function with a single input, then you just need a single Jacobian vector product to compute the entire Jacobian. All right. If instead we accumulate from the other side, then we end up with reverse mode. And here we work with so-called pullbacks. And something that's left a bit implicit here is that these Jacobians are sort of linear maps at some points of linearization. And therefore, to evaluate them, you first need to compute the full forward pass of your function, save all of your activations, to then compute the sort of this accumulation from the left side. What is very good about reverse mode is that we can compute a full Jacobian with just one vector Jacobian product if we have a scalar function. And this is the case for many applications in deep learning, where usually we have many inputs, so your parameters, and a single output, which is your scalar loss. And therefore, reverse mode is what is typically used there. So we have a quick summary slide here. So in forward mode, usually we have a single forward pass through your function. Typically, forward mode is based on dual numbers. And since we don't need to keep track of any intermediate computations, it has a fairly low memory cost. Whereas in reverse mode, we need both a forward and a reverse pass. We need to save all activations and these functions that compute Jacobian vector products. The data structure that saves these is often called tape or Vanguard list. And since we need to save stuff, it has a fairly high memory cost and overhead. So while these things apply with these input and output dimensionalities, if you have very small functions, sometimes forward mode is more efficient just because the overhead can be much smaller. All right, and from here on, Guillaume will take over.
Sorry to our YouTube viewers for the noise. Taking over the mic, and I'm going to tell you from this theory how you can actually use AD in practice if you're a package user and if you're a package developer. What are the most common pitfalls that you're going to run into when you try to make your own functions differentiable? So let's go. Why? The first question is, why do we have so many backends in the first place? I listed them all because I read all of their documentations. There's 12 or 13 of them. And one reason for that is, as Adrian explained, there are conflicting paradigms on how to implement differentiation in a computer. You can have numeric, symbolic, algorithmic approaches. So these require different implementations. Even within the subfield of algorithmic or automatic differentiation, there's various ways to do this. You can do this with operator overloading by basically defining new methods with custom number or array types. Or you can do it by grabbing the source code and just tweaking it until it gives you the derivative instead. But of course, there's another reason, which is historical. It was just developed by different people at different points in time. And so it is only normal for an open source ecosystem to have new packages emerging and some packages being, in a state of non-maintenance or disrepair. So it's okay. We have various choices, but as a beginner, it can feel rather daunting. So I'll try to help you figure out what to use. And here are the main criteria that you should take into account. First of all, if you try a certain automatic differentiation system, which I call backend, will it execute without throwing an error? And that's less obvious than you think. Does it return the right derivative? Because in some cases it might be wrong due to numerical errors or some more subtle forms of errors. And is it fast enough? But I can't stress it enough. You have to start with, does it execute without error? You can't optimize the shit out of it if it just doesn't run at all. So here's my decision tree. I know some people are going to yell at me, but I think for beginners, this is really useful. So the first thing you want to do is, usually you're not going to use AD in a vacuum. You're going to use it as part of a larger project, for instance, involving differential equations or neural networks. And if you have a neural network library like Flux, it's usually going to tell you in its tutorials which automatic differentiation backends have been tested with it and which are reliable to work with. So first thing you want to do is follow their recommendations. If there are no recommendations, if you're in uncharted waters, then you first need to choose a mode based on the input and output dimensions. Roughly speaking, if you have many inputs and a few outputs, reverse mode is great. If you have many outputs and a few inputs, forward mode is great. And within that mode, try the most battle-tested backends. In forward mode, it's ForwardDiff or Enzyme. In reverse mode, it's Zygote or Enzyme. It's an oversimplification. I know. Sorry. Deal with it. And if nothing works, fall back on finite differences, because finite differences will never betray you. Now, so that was for users. Okay, now you've graduated the Julia Academy, you're a bit more confident, you're writing your first packages, and you're wondering, okay, what if I want to make the functions I write differentiable? And then you're going to run into a series of failure, and a solid 1 hour of my life every day is dedicated to debugging float64 in ForwardDiff on Discourse. So every day there's someone who comes on Discourse with this typical ForwardDiff failure. They wrote a function here, which I call bad copy. What it does is it just copies to an array full of zeros whatever's inside the input array. And when you try to compute the Jacobian of this function with ForwardDiff, it's going to yell at you, and it's going to say, blah, 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 no method matching for float 64 ForwardDiff dual. I can't stress this enough. This is what everyone will run into first when they try to use ForwardDiff. Now, why does this happen? Adrian told us that forward mode automatic differentiation usually uses dual numbers, as you can see here. What ForwardDiff does is it tries to propagate a specific type of number through your function, which is not just a float 64. And so you have to be tolerant. You have to be open-minded. You don't have to say, okay, float 64 is my life and I want nothing else. You have to let your functions breathe a little and accept more inputs. So what's going on here? When you call this method, what it actually does is it calls the underlying method zeros of float 64 and the given size. In other words, this creates a vector of float 64. And while it would not be a problem in your usual scenario, when you try to do automatic differentiation here, this becomes an array of dual numbers. And so what you try to do is you try to copy dual numbers into an array of float 64, and of course it blows up. So what you want to do here is you want to allow numbers that have a specific type dual in your functions. And more generally, you should strive to write functions that are as generic as possible, because you never know what sort of weird magical number types people may come up with. It's not just for automatic differentiation. It's for unitful types in physics. It's for measurement uncertainties. It's for all types of things that you want to put inside your functions, and you want to get something at the end that makes sense. And if you just keep sticking to float 64, you're going to miss out on the magic of the Julia ecosystem. So here, my good copy function, it accepts any type of array of any type of real numbers, and it takes into account the element type of the input when it creates the temporary storage. And with just that, I can ensure that ForwardDiff Jacobian works as intended. So that's one example. The other one, which pops up the other half of the time on discourse, is this error. So ForwardDiff will fail because you don't allow generic types. Zygote will fail because you mutate stuff. In my bad copy function, I had a copy2 with a bang, which means it mutates its input. And here Zygote is going to tell me mutating arrays is not supported. This error occurs when you ask Zygote to differentiate operations that change elements of arrays in place. This is sufficiently explicit, but I'm highlighting it just for good measure. And so here, what you want to do is you want to either call a function which you're sure does not mutate its input, but that's not always possible. So when you have to use functions that involve mutations, for instance, for performance reasons, the right thing to do is define a custom chain rule. This is possible thanks to the awesome work of Frames on the chain rules ecosystem. And here I give you a very brief example of what it means to define a custom rule. So I define another function, badCopy2, and for this one, I'm going to tell Zygote how to differentiate it. What I'm doing here is I'm writing a reverse rule for my function when I give it input x. What is this reverse rule going to do? Remember, we're in reverse mode, so we need to, first of all, compute the output of the function, but more importantly, we need to have a way to compute vector Jacobian products. In other words, a vector Jacobian product takes a perturbation of the output and it brings it back, it pulls it back onto the input. So that's what I'm doing here. I'm defining a pullback. If I perturb my output by dy, then the corresponding perturbation of the input is going to be the vector Jacobian product, or equivalently, the transpose of the Jacobian times the vector. Okay, it just so happens that the Jacobian here is the identity. In reality, you would not code it like that, but here, just to emphasize that all we're doing is a vector Jacobian product, this is the key equation here. And so by writing this chain rule, where you compute the value of the function, but you also give it a way to work out pullbacks in the reverse pass, then when you call Zygote.Jacobian on your new function, you see that your rule is called when it tries to differentiate through the function, and the inner pullback here is called as well twice, because as we saw, we need two pullbacks when we have two output dimensions. So all this to say, when you have a function which is not supported by Zygote, most of the time you will want to either change your function, or if it's not possible, write a custom rule knowing what you know about your mathematical model. And it looks hard, but Chain Rules Core is probably one of the Julia packages with the best documentation out there. So this taught me all I know about automatic differentiation. Really read it, it's worth a try. And now you also have Enzyme, which is the kind of new kid in town. And it's like way more powerful than the other kids. But it's also, it has a bit of an attitude, right? And so you need to know how to handle it. And in particular, it has this whole mechanism around activities specification, basically saying this argument needs to be differentiated, this argument doesn't need to be differentiated, and you need to know how to work your way around it. So you'll often see errors that are linked to the way that you specify the activity of your inputs. And for that, there's a brand new FAQ in the Enzyme documentation that goes into more details on how you can solve these types of bugs. But so these were the three main types of problems that you'll encounter when you work your way through automatic differentiation. And it's important to emphasize this is structural. No automatic differentiation system is going to be perfect, handling 100% of the Julia code base with no errors. That's not going to happen. So anything you choose, it's going to have advantages and drawbacks, and you need to work with them. Now, this all started with a very late Slack conversation between me and Adrian. And one of us said, well, we need to give users a way to call automatic differentiation without diving into the documentation of every single package. And so that's how Differentiation Interface, or DI for the people in the know, was born. The goal is to offer common syntax for all of these backends so that you may switch them by just toggling an object instead of going through each documentation and figuring out, wait, is it called Jacobian or is it called pullback? How many arguments does it take? In which order? How do I parse the result? Do I need to specify activities? How do I specify the cache? How do I record the tape? Etc., etc. I know all this because I coded all this for you, so you don't have to. In advanced use, you may want to call the backend's API directly because of some subtle performance issues, but for 99% of beginners, I would say this is soon to become a good way to start auto-diffing through stuff. AD users can so compare correctness and performance between backends, and developers get access to a wider user base. How does it work? Well, first of all, it supports every autodiff package out there. All of them, and the ones that are being developed, like ADAL-C or GTPSA, are also adding support. So it's as comprehensive as it can be, and it's fairly simple. So the way it works is you're using differentiation interface, and you import any backends that you may want to use, and you define a function and an input. And here, for instance, we're going to compute gradients, which is one of DI's operators, and the only thing that changes between the different backends is this object here, which is taken from AD types. And if I want to use ForwardDiff under the hood, I say compute the gradient of this function with ForwardDiff. If I want to use Enzyme instead, I use the exact same syntax, I just change this object to AutoEnzyme. If I want to use Zygote, no big deal, same syntax. Same syntax, different libraries. And this allows you to compare their performance and correctness. Once you are done with that, you can increase performance because DI also has a preparation mechanism for things like tape recording or cache, etc. But again, that's something that the user doesn't have to dig into to figure out. I dug into it, and it only has to be done once instead of doing it for every single package out there. Now, it has several features that I want to briefly mention. It supports right now only scalar or array inputs and outputs with either one argument or two arguments, but we're going to probably work on that Saturday. It has the standard operators that you would need in your day-to-day life, push forward, pullback, and then derivatives, gradients, Jacobians, even higher order like Hessians. For the weird people in the back who want higher order differentiation, third order, fourth order, don't look at me. I won't do it. There's out-of-place and in-place versions, and you can have a few niceties like combining different backends or translating between backends. If something is differentiable with one but not the other, you can sort of translate under the hood with this structure. It also has a sister package called Differentiation Interface Test that allows you to compare backends systematically and even with weird scenarios like static arrays, GPU arrays, and it does automatic benchmarking. It has a brand new sparse AD ecosystem, which is kind of Adrian's baby, with sparse connectivity tracer for sparsity pattern detection, a few utilities for matrix coloring. The gist of it is that you compute Jacobians by computing one column at a time. But if there's lots of zeros, you can actually compute columns, several columns at a time, and then decompress the result. And that gives you beyond insane speedups if it's done properly. Now, to conclude, all of this is brand new. Like, all of this is less than 6 months old. I'm not pretending it's going to be the best performance that you can get on every single problem. What I am pretending is that we are extremely responsive. So if you want to help us get this to the level where it needs to be, try it out in your code, report bugs, open issues, and yeah, help us make this even better. Now, of course, there's plenty of things I left out. If you want to AD through a simple function, that's great. But if you want to AD through an integral, an optimization solver, a stochastic expectation, there's more stuff out there in the ecosystem, especially in the SciML world and also in my research on discrete combinatorial solvers. You can find more details in this book. The take-home message is the following. Computing derivatives is easy. It's 2024, you don't compute derivatives by hand. That's over. But as soon as you use automatic differentiations, it comes with its own limitations. So learn to recognize them, learn to overcome them, and I think you're going to have fun. We have time for questions, but not from Chris.
Okay, thank you guys. Awesome talk. Yeah, we have time for some questions. Anyone want to get us started? Raise your hand if you have a question. I'll come to you with the mic.
So thanks a lot. So I was wondering, so what's the best way, let's say I have two arrays and I want to do reverse mode automatic differentiation, and sometimes I only want to differentiate with respect to x and y, or sometimes maybe both. So is there an easy way to specify, enable, disable some of the gradients?
So in differentiation interface, not at the moment. In Enzyme, yes. In Enzyme, it's pretty much the only backend that supports this. So that also explains why DI cannot do this yet, but perhaps next week it can. So the development is really that fast. So yeah, this is on the top of my bucket list.
So maybe a quick follow-up. So I would wrap everything into a component vector if I want to use like bigger, like x and y, right? Because you only accept single arguments.
Right now, that's what you need to do. Again, I'm going to work on this Saturday during the hackathon. So the next big thing I want to do is figure out a way to pass multiple arguments and specify which of them are differentiable and which of them are constant.
While I'm walking, all you guys in the back, there's a whole bunch of seats here in the front. So in the break, go ahead and move up.
Thank you. Thanks so much for the talk. It was great. I wanted to ask, would you be able to say anything to the broader ecosystem in which order differentiation is situated? Like, for example, I found out about AD through Flux, and that meant I only knew about Zygote. I learned about Enzyme today. Is there plans for DI to kind of be integrated with Flux or Lux or any other kind of higher libraries?
Again, this is kind of a very new project, and we started with the simplest setting, which is like functions of one argument with arrays, essentially. And it may look simple, but it already covers the use cases of some big packages like optimization.jl or ordinary differential equations. So that's kind of our first target. We've been working with Chris quite closely to get the SciML ecosystem to use this. The next big target is, on the one hand, deep learning. And for deep learning, it's more complicated because the layer structures inside Lux and Flux, they're not just arrays. So that's essentially a rather hard thing to handle, because you can't pretend with 100% certainty I can handle every struct out there. The imagination of Julia developers is endless, and they'll always find something to break your stuff. So the question is not whether we can pretend to support arbitrary structures. The question is whether we can test reliably enough what we support to be useful in Lux and Flux. And it's feasible. We have the infrastructure to do it. It's just a matter of Lux and Flux defining what kind of test suite would give them confidence in the code that we wrote. Yeah, maybe Sunday, right?
Yeah. Thanks a lot for your talk and for your effort. I think a bit about all the limitations that you said across all these packages. So you have to pick and choose, but I actually find myself needing to use multiple of these automatic differentiations. So I want to, maybe just to give you an idea, I want to train a neural SDE, and I want to use Zygote, for example, but it doesn't work for my case because I need to do, or it doesn't work for specific cases like SDE, so I find myself wanting to use something else. And then I have to pick and choose between a couple of these libraries. Is this good behavior, or I shouldn't be doing this?
So if you go back to my decision tree, I'm not an expert on differential equations and the like. So this is really SciML realm. Yeah. The first answer would be use whatever SciML tells you to use. If you use a neural PDE or whatever and you're using it from a package, then do whatever that package tells you in its tutorials, because that's the way that it's tested. Now, if it doesn't work, differentiation interface is a very good way to experiment, because switching a backend is as easy as just toggling the object where you choose it. And yeah, basically, if you need to do something custom that is not covered by an existing package, open issues wherever the AD backend that you chose doesn't work, to see if it's fundamental or if it can be overcome.
Yeah, maybe one sentence on this also. So maybe what you're looking for is also this differentiate with function, which allows you to automatically generate custom reverse, forward, and reverse rules by calling other backends. So we're sort of pretending to implement forward or reverse rule, but we're actually calling another backend in the background. So that's something that maybe you would have written by hand, but that you can now use through differentiation interface.
I'm sorry, I think this is all the time we have. If everyone can give Guillaume and Adrian a hand. Sorry.